just before I get started on an explanation of these examples, please don't try to learn this example. There's nothing special about that question, or you will see that that is an identity that you do know. Or this one, for example. There's no point trying to learn that. Rather, when you're doing these questions, your focus is on using the identities that were just introduced, using them. And any other little techniques that come up, and often I've selected questions to do here because they have good little techniques in them. Okay, let's get started with the first one. Sine 3 alpha plus 5 beta. It just says expand. You know what expand means, get rid of the brackets. And the only way to do that is because you know the expansion for sine of compound angle, the sum of two angles, so you follow the rule. And that's it. Don't have to do any more. You may never see that question again. You will see you will use again this identity here, but not necessarily in the form of example 1. Example 2, use the compound angle results to prove. So what comes to mind with a proof? Hopefully you're thinking, take the left-hand side, work with it and turn it into the right-hand side. That's what you do with a prove question. So prove that the cos of 90 minus theta is equal to sine theta. Sorry. So take the left-hand side, cos 90 minus theta. What do we know about that? Now this is where you've focused on committing now to your memory the skill for expanding sine, cos and tan of the sum of two angles or the subtraction of two angles, so that when you see this situation in the future, you'll know to use the appropriate expansion. So we're going to expand that out. Cos 90 cos theta plus sine 90 sine theta. Where am I getting that from? I'm getting that from up here. We know the cos of 90 is 0. Cos of theta is called cos theta. Sine of 90 is 1. And sine theta is sine theta. Anything multiplied by 0 is 0. And 1 times sine theta is sine theta, which is actually the right-hand side. Therefore, you've proven or shown that the left-hand side is equal to the right-hand side. This is an identity that hopefully you recognise, because you've seen that since stage 5. Example 3. Again, I wouldn't spend any time trying to learn this. You may never see it again. There's nothing that special about it. It's not like it's something that you need to be able to recall automatically. No, not at all. It's prove this identity. So let's again take the left-hand side, 2 cos theta plus pi on 3. What do you see there when you write that? Hopefully you see that you've got the cos of compound angles, two angles. So we use the expansion for the cos of the sum of two angles, which is cos theta, cos pi on 3, sine theta, sine pi on 3. When you see cos pi on 3, hopefully you're relating it back to your exact triangle. So we've got 2. Cos theta is cos theta. Can't change that. But we can substitute for cos pi on 3. Pi on 3, cos is a half. Minus sine theta is sine theta. You can't change that. But we can substitute for sine pi on 3, which is root 3 on 2. So expanding the bracket, multiply this term by 2, cancels out the half. We've just got cos theta. Multiply this by 2, cancels out the 2, and we've got root 3 sine theta. And you can see that's exactly the right-hand side. So we've taken the left-hand side and shown it equal to the right-hand side. Adequate for a proof. Question 4, and again, there's no point learning that 15 degrees is 45 minus 30. It's more about why. Because there's many ways you could write 15. Why didn't they write it as 20 minus 10? Oh, sorry, 20 minus 5. Well, the reason they didn't write it as 20 minus 5 is because we don't have any exact values for 20 degrees or 5 degrees, but we do have exact trig ratios for 45 degrees and 30 degrees. You're going to find that any of these questions usually result in some combination of 30, 60, 45. So just keep that in mind. Or when they're getting bigger, it might be 180 plus 45. Or it might be 360 minus 45. So, yeah, keep in mind the possible combinations of different angles. So, by expressing 15 as 45 minus 30, show that the sine of 15 is this thing. Again, I wouldn't spend any time trying to learn that. You don't need to know that. We just have to be able to get that as our right-hand side. So it's given us a fairly big hint. Sine of, show, it's a show question. You would take the left-hand side, the sine 15. Now, we'll do with it what they said. Write it as the sine of 45 minus 30 because we know 45 minus 30 is 15. Expanding, you get sine 45, cos 30, cos 45, sine 30. It's that you're feeling very confident at this stage. Why? Because we've got exact values for sine 45 from our little triangle and cos 30 from our little triangle. Subbing them in, subbing the values in, we've got a common denominator. It's called 2 root 2, and I'm really confident with that because when I go back and check it to where I'm heading, the denominator is 2 root 2, and I've got a root 3 minus 1 as the numerator. So I was able to show that the sine of 15 is in fact this fraction. It goes on to say, and find an expression for the sine of 75. Sine of 75 would be 45 plus 30. And again, why didn't we write this, for example, as 50 plus 25? Well, again, it's because we don't have any exact values for 50 degrees or 25 degrees. But we do for 45 and 30, and we do a similar thing, use the expansion for sine, sub the values in from our exact triangles, and this time you get root 3 plus 1 on 2 root 2. Question 5, definitely a new little technique. If cos of alpha is 4 on 5, find cos of 2 alpha. Now, cos of alpha is 4 on 5. It's not taking me to exact triangles. I can see that cos 2 alpha could be written as cos of alpha plus alpha, which would mean I'd have to be able to find the value of cos of alpha. Well, I do have that. They've given me that. But in the expansion, as you can see here, there's also sine of alpha. I need to be able to work out the sine of alpha. The easiest way, if you're given that cos of alpha is 4 on 5, like I've said here, it's requiring a nice little and different technique. It is just, the technique is draw a triangle with cos of alpha is 4 on 5. So it doesn't matter where you put your alpha, draw a little right angle triangle, allocate your alpha to one of the acute angles. Alpha could have sat up there, but 4 would have to sit here and 5 over there. And then you probably recognise, without having actually to use Pythagoras, that you would have a 3, 4, 5 right triangle. How does that help? That helps because we now have got cos of alpha, and cos of alpha is cos squared alpha, and sine alpha. Well, I've jumped to cos squared plus sine squared equals 1. Let's just show that that works. Cos squared would be 4 squared, which is 16 on 25. And sine squared, sine of alpha is 3 on 5, and square it, you get 9 on 25. And 16 plus 9 is 25 on 25. Yes, it's equal to 1. And I'll just finish this video with the last example. Find an expression for sine of alpha x plus y minus sine of x minus y. You know, this is just a tedious expanding and getting like terms and just being really careful sort of question. Again, don't try to learn it. We're not learning the question. We're looking at the question and making the connection to the appropriate expansion. So sine of x plus y, look at that and go, yes, I know. I could replace that with sine x cos y plus cos x sine y, and that's what you do. Anytime you've got a subtraction sign, you're going to be subtracting more than one thing, put that more than one thing in brackets. So we've got a subtraction sign bracket, sine x cos y minus cos x sine y. These first two terms stay the same. Expand the bracket out, cross out these, plus it and minus it, and we end up with these two things which are exactly the same, cos of x sine y, cos of x sine y. So we get 2 cos x sine y. Okay, that is an explanation of those examples, and I think I'll leave the rest and talk to you about those in class.